This used to be a circumbinary planetary system with two stars orbiting around each other, and it has just been officially destroyed. Unfortunately, because these systems are very unstable, all of my stars and all of my planets have now become individual objects. Now today we're going to be talking about this idea of circumbinary planets, planets that orbit not one but two stars. We're going to try to recreate them from scratch and talk about the ones that actually do exist out there and why they actually exist and how it's even possible. Welcome to What the Math. And the first thing I'm going to do is actually go into fiction right here and click on the Lens of Ice and Fire. Now this is actually one of the coolest simulations that developers of this game made. This is their idea or their explanation for why Westeros has such strange seasons. Now what they actually propose is that maybe, just maybe, there are two stars that Westeros orbits, and if it's essentially, if this is a circumbinary planet, if it's a planet that orbits two stars, this is what would happen to its climate. I'm going to click on temperature graph right here. Where is it? There it is. And you'll notice that the seasons here are super unpredictable. The average temperature jumps up and down a lot, and it will keep jumping up and down a lot because of the fact that it orbits not one but two stars. And as you can see here, its average temperature is always very strange. And this is kind of what we also see in Game of Thrones, where winters, springs, summers, and falls are not 1 month, not 2 months long, but years long, and they are kind of unpredictably long as well. Now, I actually made a video of my own explaining what I thought about all of this, and you can check it out right here. This is where I kind of tried to use this game to explain the seasons in the Game of Thrones. And my theory was obviously a little bit different from this, but today we're talking about circumbinary planets. Now, as you can kind of see, this one is relatively stable, unless, of course, I accelerate this and wait many years. And with years, this may become unstable, but it's possible that it's just will change its orbital eccentricity a little bit, but may still stay in this orbit. Now, we actually know that these types of systems exist. There's at least a dozen we've found so far. And these systems are not as rare as you would think, but how they're created is a mystery, and I'll explain to you why it's a mystery, and I'll actually just use this simulation to kind of try to explain it to you. So if I were to add another planet relatively close to the two stars, so let's actually go in here and add Mercury somewhere closer. We're just going to slow this down. So we'll just add Mercury right here. And you'll notice that it's not actually going to, well, first of all, as you can see, it's already changed the orbits of the stars themselves, and this kind of has destabilized the entire system. And look at that, see how it already is destabilized and essentially sets everything into a very sort of chaotic motion. So that's one problem. So you cannot introduce new mass into these systems or everything will change. And the other problem is obviously that if it's too close to these two stars, it will unfortunately not stay in the same orbit. And I can actually demonstrate this better by going into a new simulation and creating a binary system out of two suns. So here we have two suns, and what I'm going to do now is we're just going to add a barycenter right here in the middle, and we're going to now add a few rings at a relatively close distance to this barycenter. So let's just say at a distance of about 10% of astronomical unit, or 10 times as close as the Earth is to the Sun, with a maximum distance of about 0.4. So let's see what happens. So there is the ring right now, and this is essentially what will happen early on in the development of the solar system. So as the solar system develops, it has these accretion disks that are formed. It has planetoids and asteroids flying around, and these eventually form into what would become a planet. And this is how our Earth and how other planets were also formed. And you would expect to see this in the creation of an early solar system. Now, here is the problem. As soon as I enable the simulation, just watch these little rocks, these asteroids. First of all, a lot of them get sucked into the stars, and many of them basically just kind of disappear. Now this may be because they weren't really orbiting properly around the actual barycenter. We can try to add them to individual stars as well, so we can actually go back here and add more of these. And we're actually going to add them to each of the stars as well. So let's add one here, and then another one right here. So now each of the stars has its own accretion disk, and let's just roll this and see if any of these asteroids actually remain in orbit. So you can see there's like a little vortex forming above. It's actually going to be interesting to see what happens in a few years' time. Now, having run this a few times already, I kind of know that after a few years, after like 100 years, there might be like one or two of these rocks flying around, which really gives you or raises a question, I guess. You know, how are these planets formed around the binary systems, around binary stars? Because as you keep running this simulation over and over for many, many years, more and more of these planets, or I guess you could call them asteroids because they're not really planets yet, would actually disappear. And if I were to add a planet here, it will obviously destabilize the entire system. So I'm just going to add actually a moon just to show you, because it doesn't have enough mass to destabilize the system. But here, oh no, this is a barycenter moon, wrong moon. And here we go. I finally was able to add a random moon just orbiting around these two stars. And let's just see how it goes for this moon. We're going to accelerate time a little bit. And what you will notice is that more and more of these rocks will start disappearing, and this moon will actually change its orbit as well. Now, obviously, if I were to place these rocks a little bit farther away, they may actually stay in orbit. And this is what's going to happen to a lot of the rocks that are actually on the outskirts here. They will actually probably remain in orbit. But anything that's too close to these stars, and specifically here we're talking about the separation between the actual planet or the moon and the actual stars, it has to be at least 2 to 4 times this distance. So basically, if the distance between barycenter and the star is this long, this has to be at least 2 to 4 times farther away. Anything closer will not be able to actually stay in this orbit. But as you can see, the moon is actually in a relatively stable orbit, and it will actually only destabilize its orbit with time and with other objects interacting with it. So creating this type of a binary star system is actually not very challenging, but once again, it's not actually a stable system. And if you decide to place more objects in here, you'll see what happens. So we're gonna actually place another moon a little bit closer. Let's place another moon somewhere right here, maybe another moon a little bit farther away, and another moon right here. So let's actually see what happens. And you'll notice that the closest moon already flew away. It was just a little bit too close to these two stars. And it's really the farther objects that will actually stay in orbit and will maintain their orbit. From all of these binary star systems that we found that actually have planets, all of them, or the majority of them, have two stars that are relatively close in mass. Now, usually it has to have a ratio of about, well, either a 1, which is basically same mass, to a maximum of about 3.7 or close to 4. So the two stars cannot be too different from each other. Also, all of the planets that did stay in the system have to be in a relatively same plane, so they actually have to line up relatively close. The only star system we found where a planet is sort of at a 5-degree angle, so which would be kind of right here. So this moon right now is a slightly inclined plane. The only reason this can happen if there is another star, if there's actually a third star somewhere in the vicinity, and this would actually create a system that would not have a same plane alignment. And now you can see my close moon has now actually disappeared, so we can kind of erase it because it showed what I was trying to show you guys, and that is, of course, that if you're too close to these two stars, you will not be able to stay in orbit. But I think the important part here is that what actually happens on these planets, and because there's so much interaction with these two stars, not only does the temperature change, but actually the axis of tilt of each individual of these moons and planets will also change. The axis of tilt, of course, is the axis around which the planet rotates. So if you look from the top here, this is the axis of tilt. Now, on our planet, on Earth, axis of tilt changes really slowly, and this of course affects our seasons, because seasons are caused by the fact that our Earth doesn't actually spin directly like this. It actually has a slightly inclined axis of tilt that's about 23 degrees on Earth, and here, this is what causes seasons. Now, if you're actually orbiting a binary system, if it's a circumbinary planet, its axis of tilt will change super fast and a lot, which obviously means that, unfortunately, this is not represented well in the game, but this would mean that a planet orbiting these two stars would have some crazy seasons, and they would change as much as every hour or something. So it's very likely that these planets, if they're habitable, would have some really unusual temperature changes and climate changes, and it would be very difficult to survive on them. But nevertheless, what we are going to do, as always, is try to create a planet that we can actually terraform around these two suns. Hopefully this will not destabilize the system if I add a planet, but we're going to add a random rocky planet and see if we can actually terraform it. And the reason why I'm doing this is because of all of the actual planets that we've found so far, specifically with Kepler telescope, which is responsible for looking for planets nearby, and when I say nearby, within 1,000 or so light years away from our planet. All of the Kepler found circumbinary planets, all of them were actually within the so-called habitable zone. If I show it to you right here, it's the green zone where you can actually have life or liquid water, and things like things that you need to create life would be all located in this green zone. This is where Earth, Mars, and Venus are as well. And so this zone is really important for us because that's where a potential colony or colonizable planet would be located. And every single major planet Kepler has found that was orbiting two stars was actually in this region. There is no planet that has been found closer, no planet that has been found farther away. They're all in the green zone. So maybe, just maybe, circumbinary planets would be the first priority for us to colonize. Of course, the problem here would be the climate. So we're going to place a random rocky planet, hopefully without destabilizing anything, because otherwise we have to recreate this again, right in the middle of the green zone. Habitable zone. It's called Tumnus. That sounds good. And Tumnus right now is orbiting just fine. Perfect. Nothing lost its stability. And so obviously this will change with years, because what happens after a while is a lot of these planets will start interacting with each other and acquiring eccentricity of orbits, and then if ever they come too close to these two stars, they'll get thrown out as our moon did. But we're gonna just avoid that for now. We're not gonna accelerate time too much. We're going to go to Tumnus, which is the name of our first planet, circumbinary planet that is going to be colonized. And now we're going to try to change its parameters until the temperature, and oh wow, it's already really hot here. Let's actually place it a little bit farther away. I think I placed it too close. Or no, we're actually going to change something else. We're going to make this temperature relatively comfortable, about 12 to 15 degrees Celsius, and we're going to make it colonizable planet. And the first thing I'm going to do is change its mass closer to the mass of Earth, because first of all, we want it to be smaller. Second of all, we actually want it to have lower gravity. We're also going to go into the surface pressure and change it to 1 atmosphere so that it's closer to Earth. We're now going to decrease its emissivity so that the greenhouse effects actually decrease as well, and increase its albedo a little bit so it reflects more light, so that its surface temperature actually starts decreasing. We also made it spin a little bit faster so that it actually has a night-day cycle, and the temperature here is decreasing. Let's actually see how low it goes. I'm going to change it to 20. Okay, so it's going to be more than 20. We need to definitely increase the albedo, and looks like right now we actually have a planet that is close to 15 degrees Celsius. It's slowly increasing, but I'm not sure how high it will go. I may actually increase albedo just a little bit until about 70, maybe 80%. That means it reflects about 80% of light, and you can see it's already started to decrease. Its greenhouse effect changes dramatically. Well, not dramatically, but it does change because of the fact that there's two stars, and here radiative power, as you can see, goes up and down a lot. That's basically the amount of light it gets from the two stars it's orbiting. Now that's obviously seasons, so seasons here are going to be ridiculously fast. You can kind of see that if I were to change this to 1 day per second, approximately 1 day per second. Almost every day you get a different season, so it would definitely be very difficult to survive on this type of a planet unless you like to change your clothing almost every hour. But it would be really interesting to see what this planet would actually look like, what this planet would feel like, and for this reason we're actually going to give it a little bit of water, so because we want to have oceans and we want to have clouds here. And we're also going to just kind of make this simulation run for a few more years just to see what happens to this planet later on, because its orbit might actually change with time, and it also might even change its axis, so it starts spinning in a completely different direction, although I'm not sure if that will occur, but we'll see what happens. So let's just run this for a few more years and come back to this planet after it's stabilized everything. Alright, so it's been about 2.5, maybe 3 years now, and what I just wanted to show you is the graph. So this is the radiative power. You can kind of see that not only is there daily season, there is also what seems to be annual season, which is basically because the planet is orbiting these two stars. And this is the temperature on this planet, so it goes up and down so much, and it changes a lot. It changes pretty much every week, every day, every month, and it is quite predictable. But at the same time, depending on how this planet is tilted and depending on the actual eccentricity of the orbit, this might be a lot different. So if I were to change the eccentricity, it would obviously change dramatically. And the other thing I wanted to actually mention is try to see how many rocks or how many initial asteroids you can find from the ones we've placed. We actually placed 7,500 asteroids, and if this was a singular star, all of them would actually have remained, they would still be orbiting, they would still have remained their orbit, they would be around one of the stars or both of the stars. But because this is a binary star, and because I've placed them around a binary system relatively close to the two stars, there is maybe 5 or 6 I see flying around, and they will also disappear with time. Most of them will actually probably get ejected into the outer system, or basically into the outer space, just as the ones you see right there on the border. They're flying away from us. Now the moons here are in a stable orbit, but how long the stability will remain is uncertain. But they've definitely changed their orbits a little bit. So if I were to click on each of these runes, each of these moons actually has a relatively different orbital velocity that changes quite a lot, and this obviously shows you how it orbits around each of the stars. So this is the orbital velocity change, and it's pretty hectic, pretty crazy. So with time, this will actually change to the point where it might either get ejected or it might end up in a very eccentric orbit, but it may actually stay here for millions and billions of years. So like I said, it is quite unpredictable, and it would be very difficult to try to estimate or try to predict what's going to happen to each of these moons and planets in the future. And if we go back to Tumnus now, you'll notice that the temperature actually decreased again, and so now the surface temperature is at 6 degrees Celsius, even though it was at a stable 12 degrees Celsius. So once again, the climates and the temperature on these types of planets would be interestingly unpredictable. But this is what it looks like. I'm going to slow down time so you can see it. This is what our beautiful terraformed circumbinary planet looks like. It has continents, it has water, it has all of the ingredients of life, and if we actually look at its life chance and similarity to life, you can see its Earth similarity is 95%, and the chance of life is 73 or close to 74%. So it's very likely that there might be life on these planets. It's very likely that we might one day even settle on these planets and be able to live here. But you need to enjoy the changes in climates, because it would be hot and humid in the morning, and possibly cold and snowing in the afternoon, and possibly hot and humid in the evening again. So you do need to bring a lot of change of clothes, and do change your wardrobe a lot. And so if you go back to the science fiction movies where we get to see these circumbinary planets, like for example in the Star Wars, planet of Tatooine is orbiting these two stars. Tatooine should be more unpredictable. It should not be just a desert. Technically, it would more likely be a planet that has very unpredictable seasons. And the other TV show that I know that has a circumbinary planet is Doctor Who. In Doctor Who, there's actually a planet called Gallifrey, where Doctor Who is from. that I believe it disappears in time or something, or it gets frozen in time. But before it gets frozen in time, it actually does orbit 2 stars, so it's a circumbinary planet. And maybe one day we'll actually recreate this in Universe Sandbox 2 as well. But for now, I think this is going to be the end of this video, and I hope you guys enjoyed it. And if you did enjoy it, don't forget to like it, don't forget to share it with your friends, and subscribe if you still haven't, because there's more Universe Sandbox 2 and more space videos coming in the future. And as I accelerate time, notice how the temperature actually does decrease. It suddenly started dropping below the point where it was before, and I'm not sure why. This could be any reason, possibly because of albedo, possibly because the orbit has changed, or possibly because this is how circumbinary planets are to begin with. It's just very, very unpredictable. If I were to accelerate this for millions and millions of years, we would notice that with time, things just go very, very hectic, and things go completely wrong for this unfortunate system. Now, as I mentioned before, these are real, they do exist, and we do know about them. And it would be very interesting to actually have a picture of what orbital systems do look like in here, and what actually happens to these planets. Maybe one day we'll find out, maybe not. Anyway, thank you so much for watching. I'll see you in the next video. Game you later, and bye-bye. And it looks like I just found the last of the asteroids that I originally placed. It's orbiting one of the suns right here. There it goes. So that's also another possibility, that some of the things might be orbiting really close to one of these stars. And that's all I wanted to say at the end. Bye bye.